Hey everyone, I'm Sujit Joseph, Principal Engineer at Cisco. I'm also the Chief Architect for Enterprise Search at Cisco. Got around 18 years of enterprise search experience.
Hi everyone, I'm Vishal Rao. I'm a data scientist. I have over 11 years of experience of working in AI and ML projects. Since the last 3 years, I've been focusing on enterprise search.
We'll talk about how Cisco, which powers the world's networked economy, is revolutionizing its enterprise search platform with AI and Elastic. I'll be talking about the architecture and a couple of search and recommendation use cases which are using this platform. Think about it for a moment that you are searching for information online and it takes ages for the results to load. Frustrating, right? Imagine if your company's support engineers are trying to search on millions of historical support tickets, and if the results returned are not relevant, it would not only be a frustrating experience, it would have been a huge productivity loss for the company, impacting issue resolution times, CSAT rating, etc. Well, these were some of the issues that we had with the legacy search platform, and we did indeed reinvent search, and we'll see how. We'll talk about the transformation of enterprise search. With this new platform, we saw up to 70% faster response time for Cisco.com search, which is deployed in the cloud, GCP, across the globe. We also saw 5x faster response time, especially in APJC. With this platform, we've been seeing new documents coming in to our index in just 2 to 3 minutes of index latency. Our users are finding the results more relevant. We have a new deep QA solution which actually searches for passages within the document so that we can lead the user to the direct passages within the document with the right relevant information in it. Now that we've been able to give our users the ability to find the right document in the least amount of time, what that meant is we improved the employee productivity lots. You can see that for our support search portal, that is topic search, that is used to solve 90% of Cisco's customer ticket. With the improvement in the search quality, we saw that we were able to save 5,000 support engineer hours per month. And we got raving reviews on this new platform. We'll see some of them. You can see that the results are indeed accurate and they allowed it. The speed is under change this issue. Let me talk about the scalability of this new platform. We receive 1 billion queries every year. We got almost 1.3 billion records searched with 195 million documents searched. This is across 60 plus enterprises applications. Now in GCP we have 34 Elasticsearch clusters with around 500 Elasticsearch nodes, and this is deployed on top of ECK, Elastic Cloud and Kubernetes. We also have Elasticsearch as a service on-prem used by the internal Cisco customers. We get on 1.7 billion queries every year across 80 plus enterprise applications. It has a total of 27 billion records in it. And we do support 400,000 plus document per second ingestion rates. These are on 62 Elasticsearch clusters with a total of 277 Elasticsearch nodes. They're running on Cisco UCS C240 M5 series bare metals. This is deployed on Elastic Cloud Enterprise. Now let me talk about how we build a scalable enterprises platform in GCP. Here is the architecture for it. You can see the content, some of the content resides on-prem, some are accessible from the cloud. Some of the content management systems like Adobe Experience Manager uploads the document as and when authors publish documents, and they get uploaded to Google Cloud Storage automatically in real time, and the GCS reference URL is sent to PubSub, which is sent to the document processing pipeline, which is data flow. Now we have standardized all the pull connectors as Apache Spark jobs. For on-prem, we have an on-prem Kubernetes cluster using a Spark operator to run all the Kubernetes Spark jobs. For the connectors that is running in the cloud, that is GCP, they're running as Dataproc jobs. We even have a crawler, enterprise crawler, which runs on Spark, which is based on open source project. Now, all the content is across all the connectors. They're all stored in Google Cloud Storage. The reference of all of its URLs is sent to PubSub, which is again picked up by Dataflow for document processing and business logic and relevancy signal additions. We have the output of Dataflow flowing into the AI pipelines for things like passage extraction, chunking, embeddings generation, question generation, etc. And all the processed documents, as well as the embeddings and the AI signals and the questions for the auto suggestions, etc., get sent back into GCS and PubSub, which are picked up by Logstash, which are running as microservices in GKE, Google Kubernetes Engine, across the two regions that we have in R1 and R2, that is US and Asia. And they push the data into Elasticsearch, which is running as stateful sets, again in GKE in both the regions, and it's deployed using the ECK operator. On the same Kubernetes cluster, we have the AI and the search, UI, microservices, etc. Now, these two clusters are connected together using Istio as a service mesh, and the various Istio ingress gateways are the NEG for this Istio ingress gateways are front-ended by the HTTPS load balancer, which is exposed to the end users or the API gateway layers. Now let me talk about a few of the AI-powered search use cases across Cisco. The first one is the reimagined topic search, which is a support search portal used by support engineers to solve 90% of the customer tickets. This tool searches on historical customer cases, product bugs, knowledge articles, Cisco.com, and 40 other data sources. And we receive almost 2 million support cases per annum. We roll out advanced AI-based relevancy. We've enabled near real-time indexing and advanced little search capabilities, because some of the other messages that the users use are like cannot be tokenized. We got advanced tokenization enabled. And the output of all of this is accelerated case resolution. And we talked about 5,000 support engineers saved per month, etc. Here is the UI. And you can see that it has got an ability to search on past 3 years of data or all time. Essentially, it's past 3 years of any content that has been clicked in the UI for the past 1 year are part of the hot indices, which are 100% memory map, which is almost 10 terabyte. The rest of the content is in the warm indices, that is around 16 terabytes. And as and when users interact with the content, we move the data between the hot and the warm indices. Now, reimagined topic search receives around 12 million queries every year. It's got around 20,000 users and 52 million documents searchable across 44 data sources. And these documents are pretty huge, in a couple of MBs. It includes bugs attachments, they're pretty huge, etc. Some of the AI features that we rolled out are one, the Elasticsearch query itself was formed as an output of a Bayesian optimization algorithm, which could predict the right query given a range of values for the boost, etc. We use custom algorithms for key phrase extraction. One is using fine-tuned BERT embeddings on our content, as well as using GenSim, and we used DeepSeek, that is using the BERT attention weights of the keywords to create custom query formation, etc. We have GenSim-based synonym extraction. We have graph-based ML algorithms to enable the contextual scope search. We have resolution summary snippet extraction using AI, etc. Now, rather than the user searching and trying to search for using keywords, we were trying to see, can we automate the generation of the queries and automate the searches on behalf of the users now that the results quality is good. And we used key phrases using BERT embeddings as from the support tickets, as well as generative AI. It's been a recent trend. So we use T5 based language models to generate search queries given a support ticket that is surprisingly accurate. These queries that then are used to generate content recommendations in real time as and when new cases and tickets are formed, and we use Elastic to use these queries to hit Elastic to generate those results, and the results thus retrieved are cached in GCP Firestore, and they are ultimately served using an API. And I'm also trying to create a new model that is based on FLAN-T5 11 billion parameter model. We expect much better quality predictions with that model. The next use case is AI Research Assistant, or IRA, which provides a similar support request suggestions capability. Essentially, it is semantic search on historical support tickets by creating a variety of embeddings based on the different fields of the SR. So as you can see, there are different multiple embeddings created from the case nodes, problem description, resolution summaries. Ultimately, we do a KNN search between the TAC, the SRs that are currently worked upon by the TAC engineer, support engineer, again, and take the embeddings of that in real time and matches it against all the historical embeddings from the historical support tickets, etc. And all of them are being done in real time. They are cached and they're served using an API as well. So we ultimately do a KNN search against the 5 million SR corpus with KS10000. Now, the summary you see on the top are developed using an AI model. It's a bot-based model that is being used. The next use case is BARC alerts ranking for SR attachments. So there are alerts that are generated using known digital signatures for parsing through the case attachments. Now, the problem was, how do we rank these different alerts that are generated from the case attachments in the context of the case content? And that's essentially what we solved using a semantic search. I'm doing a semantic search between the SR's embeddings against the alerts embeddings. So we generated embeddings out of the alerts and matched it against the SR case content. We created fine-tuned BERT-based embeddings from both the alerts, historical alert, as well as the case data to do this comparison. And they're being, key phrases were also being used to generate, because the email nodes are pretty huge. So we use the key phrases and generate embeddings out of the key phrases to have a shorter embeddings, a shorter text input for the embeddings. The next use case is Cisco.com search. So as you can see, we have the Q&A solution deployed, which would search on passage chunks rather than the entire document itself. It is deployed across US and Asia, GCP regions. Some of the relevancy improvements that we did were using the DeepCT, that is using the BERT attention weights of each of the keywords and use that as relevancy signals. UniLM based neural models we used to generate questions from the passages, and those questions would go as type heads as well. And ultimately we have a squad based model which would do the answer extraction from the passages given a query. And finally, we have OneSearch as use case. OneSearch is Cisco's intranet search. Here, as you can see, we have a search that enables findability on directory, places products, documents across Cisco. It's implemented as a federated search, and the ranking between the different federated search sections is done using AI models. We use deep QA in there, and we have embeddings based similarity for the auto suggestions as well. We use generative AI for question generation from these passages as well. And my colleague Vishal will talk more about the deep QA use case within OneSearch.
OneSearch is a search engine for Cisco employees which gathers data from multiple data sources and presents the results in a single view. We came up with the idea for Deep QA when we were thinking of ways to simplify the way people accessed information. Deep QA has two major objectives. First is to provide concise answers directly in the search page. The answer snippet recommender is used to provide users with bite-sized information right at their fingertips. The second objective is to provide users with a guided search experience and help them frame questions better. The type ahead FAQ recommender and similar questions recommender help achieve this. I'll walk you through the experience of a typical OneSearch user, and let's first understand how the type ahead FAQ recommender works. When a user visits OneSearch and starts typing a query, we recommend FAQs which are similar to the entered text as type aheads, and if a user were to click on one of these type aheads, the answer to that FAQ is displayed right below the search bar. This helps users frame questions better, and additionally, these recommended passages are highly relevant because these FAQs are generated or extracted from these passages. We have built an extensive database of FAQs using a combination of rule-based techniques and deep learning models. We first extract questions from FAQ documents which are directly available. We also generate questions from passage headers. The deep learning approach involves two steps. The first is to generate questions out of input documents using a T5 deep learning model. And the second step is to identify the sections in the input passage which answer these generated questions, and this is done using question answering word-based models. Here's an overview of the type ahead FAQ recommender. During the offline document ingestion stage, we first generate and extract questions from the input documents. We then generate embeddings for these FAQs, and the information of these FAQs, their embeddings, and their associated documents is stored in an Elastic index. And during the inference stage, when we get an input query, we identify the FAQs which are most similar to the input query using a combination of HNSW and BM25 models, and the FAQs which meet a given similarity criteria are recommended as type aheads to the user. Now let's understand how the answer snippet recommender works. This component is used when a user enters a query that does not match a type ahead, and at a broad level this involves three steps. First, we identify the documents which are most similar to the input query. We then identify the passages in these documents which are most relevant to the input query, and finally we highlight the most pertinent sections in these passages. Let's first understand how the document recommender works. We have a hybrid model which uses multiple information like the user's click history, the semantic and keyword similarity of the input queries and the target documents, and certain document attributes. There are three child models which identify the most relevant documents, and these are re-ranked by a classifier. Let's first understand how the click-based recommender works. The basic idea here is to recommend documents which were clicked for similar queries. So this involves two steps. We first identify the past queries which are most similar to the input query, And then we rank the URLs which were clicked for these past queries. So how do we identify these similar past queries? This is done by generating an embedding for the input query. This is done using an expert model which is deployed in NVIDIA Triton. We then do a k-NN lookup on the past search term index, and this index contains information of the popular search terms from the past, the embeddings of these search terms, the number of times these search terms were used, and the distribution of clicks across different documents. So for example, like let's say a person enters a query like PTO, and we identify similar past queries like PTO US, PTO, and PTO tool. And when these search terms were used in the past, let's say documents U1, U2, and U3 were clicked, we finally generate a score for these documents based on three factors. First is the fraction of times these documents were clicked when the past search terms were used. Second is the similarity of these past search terms and the input query, and we also use information of the popularity of the past search terms. So let's say based on this formula, U1, U2, and U3 get a score of 0.3, 0.6, and 0.1. So the recommender will assign a rank of 1 to U2, followed by a rank of 2 for U1 and a rank of 3 for U3. Our second child document recommender is the semantic document recommender, and this recommends documents which are semantically similar to the input query. During the offline process, we first split a document into multiple elements. Each document will have a title field, a meta tag field, and it will contain a header and body for each of its passages. Then as a part of the processing step, we generate an embedding for each of these document elements and also determine the regions where these document elements are applicable. All this information is stored in an Elastic index. And during the inference step, when we get an input query, we generate an embedding for the query and identify the top similar document elements using HNSW, and we also apply a region filter. We assign a score to a document based on the cosine score of its most similar document element. So for example, like let's say document D10 has a cosine score of 0.6 for its title, a cosine score of 0.4 for its meta tags field, and a cosine score of 0.9 for one of its passages. So in this particular case, the passage has the highest cosine score of 0.9 and document 10 gets a score of 0.9. So let's say based on this approach, we identify the top documents as D10, D20, and so on. So these get recommended as the second set of recommendations. The third child document recommender is the keyword document recommender. And this is very similar to the semantic document recommender, except for the fact that we use a BM25 model instead of HNSW. Now that we get the top document recommendations from each of the child models, the final step is to re-rank these documents. And this is done by passing information of these documents to a classifier. The features of these documents are generated based on the intermediate scores generated by these child recommenders. So we get information of the score and rank of the document from each of these child recommenders. And additionally, in the case of semantic recommender, we also get information of the cosine scores of its document elements. We also use some features of the document like the click-based popularity and document recency. Document recency is an important field because it helps offset the bias that the click-based model has towards older documents. These features are fed into a classifier which generates the final predicted score, and the classifier is basically an ensemble of 5 LGB models which have been trained on users' historical click data. Now that we have identified the top relevant documents, the next step is to identify the passages in these documents which are most relevant, and this is done by identifying the passage in a document which has the highest cosine similarity with the input query. We then highlight the most pertinent sections in these passages, and currently this is done by highlighting the common keywords, and we are also working on a deep learning model which will automatically identify the most relevant sections in a passage with respect to the input query. This concludes our section about the answer snippet recommender. Now, there may be cases where a user may enter a query which may not have sufficient information, and DeepQA may not be able to discern the exact context. Let me give you an example. Like, let's say there's a user who has an emergency at home and he's planning to take a few days off. He may visit OneSearch to understand more about this process, and he may enter a query like PTU. DeepQA may recommend this passage which has some general information about PTU. But this may not completely answer the user's query because it may not elaborate about the process of taking time off during emergencies and what you do in such a situation. We try to solve this problem by trying to inform what the user meant based on the passages which he interacted with. So in this particular case, when a user clicks on show more or hovers over this particular section, we recommend additional passages which are similar to this passage. We do this by passing information of the passage which he interacted with along with some contextual information from the original query to the answer snippet recommender, and we get these additional results. In this particular example, the critical time off page contains information about time off during emergencies, and this answers the user's query and we have satisfied user. So finally, what's the impact of this solution? This has helped significantly improve the relevance of our recommendations. There has been a 30% improve in the mean reciprocal rank metric and a 23% improvement in the NDCG score. And these metrics have been computed on an evaluation dataset prepared from users' click history. Thank you.
Recently, you've seen the reinventing of search and Bing, Google with ChatGPT-like experiences. Well, we are starting a similar journey with generative AI models and search. When you combine the speed and accuracy of Elastic and the power of Google Cloud and generative AI, you can build the most stable and cost-effective enterprise search platform which delivers the most delightful experience for our end users. Thank you.